Okay, so that looks clean to me. Now I started up my NMR. So I'm gonna run an NMR of this sample. And so, but first I'm going to run just the standard sample to see if this instrument's looking good. So I need to get something in here running. So I'm gonna run, say, use my spinner. Remember the fat end is up. And I'm going to use this ethyl acetate, concentrated solution of ethyl acetate. Let's see what that looks like. Make sure the instrument's running okay. I haven't run it in a long time. I'll try to do this one-handed. I'm going to try to set this up. I don't want to touch the spinner, remember, because the spinner has, it has to be clean, because if it gets oils from my fingers on it, then those oils can collect dust and get the tube, the probe tube dirty. And when it's dirty, there's more friction. And when there's more friction, it's less likely to spin. Okay, so let's see if I can get this in there. Oh wait, oh, this thing's too low. Time out. I don't have enough sample in here, it evaporated. If you remember, we need at least about 3.5, 4 centimeters of sample in here. So I'm gonna assume I have enough ethyl acetate. Actually, before I do that, let's see if I have another sample that seems to be full enough. I'll get some other samples in there. That's water, of course. It's that full one. That looks like a good full one. What is this? Methyl salicylate. That's a good one. Let's do that one instead, because otherwise I'd have to go get some methyl acetate, which wouldn't be a big deal, but methyl salicylate's a cool one. Okay, so oil of wintergreen, methyl salicylate. I'm going to run that. That's got enough solvents in it, a liquid. Let's see if I can do this one-handed again and not touch. Got it. Dun, 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 dun. Okay, I need the spinner at the correct height. I use the depth gauge here. Carefully push my NMR tube in there. And when it hits bottom, it should be at the right height to spin. So I'll set it here. Floating on air again. It's been a while since you've seen this, huh? And then I press and hold inject. Actually, that inject button has like a faulty switch, huh? I'm going to do the other method. I'm going to hit off to get it to drop down. So I'm about to press off, and then now I just hit off, so the airflow that was keeping it up stopped. And now I'm going to look in there. It's looking really good. See how you can read the? It was looking good. What did I do? See how you can read the numbers on top of the cap? When I turn the air back on, it should start spinning and blur those numbers. There it goes. All right, spinning good. Sometimes getting your sample to spin is the largest accomplishment. And we are spinning. So close the cap, keep the dust out. Come on over to our Nmr software. Remember, that's where we collect our FID, our raw data, the AII Nmr. I'm in the proton NMR setting. H1 displayed down there, and it says nucleus H1, and this is a 60 megahertz NMR. So let's take our first scan. We'll start off, always by doing a proton NMR first. So the command for scanning a proton NMR and a carbon NMR to start a scan is Z, the letter Z, and G. And then you have to hit enter to start it. So see, I have Z and G in the command line, but nothing happens until I hit enter, and it asks me to save it as a name. Use that default name. It's PNMR FID, free induction decay. So I click save, or when I want to be quick about it, I just hit enter. So it's pulsing all the radio waves at our sample, exciting all the hydrogens, and letting them relax. Oh, we got a nice FID. Looks like the instrument's working well. Let's bring this FID over into the nuts software. Here's the nuts. We're gonna go nuts. This is the first time you open it, you gotta say okay. And now the command to bring it from the FID from the Nmrc software into NUTS is the letter. The commands are up here on top of the printer. If one day you get to come in, the NUTS command is A2, the letter A and the number 2. And when we do this, we don't have to hit enter. We just hit the letter A, the number 2. It automatically comes over, and oh, there it is. Yeah, it looks like things are a bit off. So let me draw for you oil of wintergreen. It's a methyl salicylate, right? I'm gonna make sure I get this right. So oil of wintergreen. It is this, I believe. You know, I'm not 100% sure right now. I think that's oil of wintergreen. But I'll double check that. But anyway, I think this is right. I think this is the OH of the phenol. What is it? The methyl might be on this position. But that's okay, we'll find out. No, the methyl's there. It would be, OH would be at 12. Well, let's do this. These should be aromatics right here. This should be in the aromatic region, and it's not. It's between, it's about 1 in the middle of it. So this, instead of these signals being at 1, they should be down around 7.5. So what I'm going to do is I'm going to go and I'm going to fix that with the frequency offset command. We type the letter F and the letter O, and then, oh wait, I don't do this in, see, I just typed FO in that sense. Like, what are you talking about? It's because I don't do it there. I have to do it in the Nmrc software. So once again, I got to type F and O, and then I must hit enter for anything to happen. I hit enter in this software, and it says enter your current position of your reference. It's not my reference TMS that I'm moving, but I know that there is a signal. The aromatic signals are at 1 currently, so I'll put 1, and I want them to be at about 7.5. This will get my spectrum more close to where it should be, but not perfect, but good. I hit enter, and now I still won't see this change in the PNMR because this is the old data. I need to collect new data. How do I collect the new data? ZG, enter, and then it's asked me default name. I hit enter again and accept it. There it is. Let's bring this new data, this new FID over to NUTS. I do that with the command A2. Oh, yep, that's much better. Oh wait, yeah. I think the structure, yeah, that's at 4. Yeah. Well, no, I think I have it right. Wait, is oil of wintergreen this, or is it? No, it's methyl salicylate. Yeah, it's not this one. It's this one. I'm gonna double check on my phone. I'm gonna look. I guessed right the first time. Methyl salicylate is oil of wintergreen. If I take this methyl here and I replace it with a hydrogen, it's salicylic acid. And if I keep the hydrogen like I just changed and I put a methyl here, or I put an acetyl here, I got aspirin. Okay, so we got our methyl salicylate, and it's looking pretty good. TMS is not quite at 0, and it's not really a singlet, so that means I should shim it. But I wasn't really that concerned about this spectra. I just wanted to see the NMR was working. So I'm going to prepare my other sample, and I'll shim it and set TMS to 0. This was just the first run. Looks good though. Now I will eject that sample of methyl salicylate so I can put in my others. And the way I do it is I gotta have my chem wipe over the opening so that it will not, the sample when it comes up, it won't pop out and break the glass. So I'm going to run into my hand via the chem wipe, and I need to press eject. So I'm going to press the eject button with one hand, and maybe my video will see the other hand. My one finger. Yeah, there it is. It just came up. Got it. Got it out. And now I'll take it off with the camera off. Now I'll prepare a NMR tube with a saturated solution of the neutral compound benzoin. We figured out it was benzoin in with the IR. So the first thing I'll need to do is not put it right in the NMR tube, but put it in a test tube, which I've labeled at 1/2 centimeter up. I want to use about 0.1 grams. So first I'll zero out the test tube in a beaker holding it. Then I will add my crystallized benzoin. I didn't mention when I was taking the IR that I don't think I have much, if any, dibromobenzene that I was trying to crystallize away in it. The IR is not the easiest thing to tell that sort of thing with, but I could look for bromine signals in IR. There's a carbon-bromine bond in the fingerprint region we can look at. I can talk more about it in the Google Doc if I remember. The NMR it will help us know if we have bromobenzene too, because the integration will be off, but let's see how much I got now. About halfway to where I want to be. I want to be about 0.1 grams or 100 milligrams. Put some more of these pretty crystals in there. The benzoin crystals. It was weird to see those little black specks in the benzoin with the microscope. I wonder why that was. I should try it again. I don't see them here, but maybe it's just because I'm not close enough to them. In the NMR, if there's impurities, I might see them too. So got now. Okay, close enough. 0.0950 grams. I'll notate that. 0.0950 grams of benzoin in NMR prep tube. Pen's dying. Okay, so now I will take this over to my NMR solvents, and I'll do the same thing. I'll add deuterated chloroform, but not too much this time to start, and then add some deuterated DMSO to try to get it even more concentrated. Okay, here's my deuterated chloroform. And my benzoin. Let me drop some deuterated chloroform, put it back, draw it up, put it back. And now I want to do it to just under the, I think I want to go under the line, so I'm going to be more careful this time, just dripping. Okay, let's see. That's under the 1/2 centimeter line still. Put a few more drops, see how that looks. Still under the line. A few more drops. It's dissolving, I think, but not all that much. Now I'm gonna go order bottle service. Get the bottle of Dom Perignon over here. It's a big night. And I'll add, what I'm referring to is the deuterated DMSO. I need to go get a pipette for it. Okay, I'm back. Okay, here's the good stuff. I'll try like 3 drops to start. Can you see this? 1, 2, 3 drops. Let's see what that does. Looks starting to dissolve a little bit, maybe. Let me do another 3 drops. 1, 2, 3. And again, when you're attempting to dissolve things with deuterated DMSO or just DMSO in general, you should give it a little more time than you think. Sometimes it will dissolve, but it's just slow. Yeah, it's definitely dissolved more. I'll do another few drops. 1, 2, 3. So I got 9 drops in there so far. I'm going to try another technique too. I'm going to get the blow dryer, but I need to do that in the other room. I think if I do the blow dryer in this room, it blows the circuit. Conair Cord Keeper 1875. Let's see if this can help us out. It's going to be a little noisy, but we'll try to see if it does. I think it's definitely helped. Yeah, it looks like it's almost all dissolved now. Hard to give you guys a view of this where you could tell exactly what's going on. Let me see. What if I put my hand right by it? Easier to see. It's pretty warm now, and it looks like it's good. Still got a little bit of crystals not dissolved, so it's not it is saturated still. So I'm gonna pipette it into my NMR tube, which I think I left in the other room. I'll be right back to grab it. Okay, this is going to come out well. Using the bottle surface really makes a difference. Getting the big good stuff out. Since there's only me doing this experiment, it's not too expensive for one version of this, but if you were all here doing this, it's a bit more pricey for everyone to be using 9 drops of deuterated DMSO. Let's see how this goes. Yeah, this is looking great. I put a line at the 4 centimeter mark on my NMR tube, and I'm right about at that line too. Let's see, where is it? Yeah, it's right at the 4 centimeter line. So yeah, I did a good job there. Didn't use too much NMR solvent this time. I'm gonna cap that and bring it over and take the NMR of it. Okay, let's see if I can do this. One-handed, got it. Just the height with the gauge there. Then put it in the probe and turn it off. Turn off the airflow so it'll sink down. Turn the airflow back on. Hope for a spin, and yes, it's spinning again. Getting lucky today. Close the lid. And let's come on and over and run. What first, proton or carbon? Always the proton first. And I was doing a cozy and other things. I'm going to do an NU space H1 just in case any of these parameters got changed. If I do NU H1, it sets it all back to default. Now I want to scan, so I go ZG, enter, and then accept that default name, enter again. Wait about 8 seconds, and I'll bring it into nuts. And yeah, oh, it looks funky FID. I wonder if the TMS is off. Let's check. If I go A2, I'll bring it over. Oh no, wow. FID look weird, but I got a lot of signals here. Oh, this is great. I like this a lot. This came out really well. Very good. TMS looks good too. I almost don't want to shim it the way it's looking, but I don't know. I'm going to do it anyways. Let's do one. So the TMS is at negative 0.089. Let me fix that first. I take F. O, enter. Negative 0.089. Enter. It should be a 0. Enter. Oh, and then I'll start rescanning this. Oh no, I was going to shim it, yeah. S-H-I-M, enter. 2-second relaxation delay, let that shim. While it's shimming though, I'm going to look at the pre-shimmed spectrum here. This thing looks great. I have shimmed, I set TMS to 0, and now I'm rescanning it. Alright, bring it over to nuts. This is the old one, pre-shim, A2. Yeah, it's looking even better. Looks good. Nice. I'm going to make my text box a little prettier. Move it over here, hit enter to get out of that. I'm going to zoom in around my peaks by double clicking. Drag a box, right click, hit enter to get out of that. And O to get back to my text box. I'm going to make this a little prettier. Okay, I got my spectrum labeled, and now I want to integrate this this one like I did the last one. I'm going to hit C to clear all those last ones, get some nice clean cuts on these integrals. So I go 2 clicks on one side, 1 click on the other, 2 clicks on one side, 1 on the other, 2 clicks on one side, 1 on the other, 2 clicks, 1 click, 2 clicks, 1 click. And I'm going to label this one as, this one looks pretty clean. I'm going to label this one as 1. So if I go V, I should hit 1 for that. Okay. Yeah, this looks really good to me. So let me show you benzoin again. So let's show you what I'm talking about. So here's benzoin. And I'll draw it up with the intermolecular hydrogen bonding again. So benzoin has 1, 2, 3, 4, 5, 6, 7, 8 groups of hydrogens. Around the aromatic ring, the 1, and then this makes 2, 3, 4, 5, and there's 5 on this side, 2, 4, 5. These 10 should show up in the aromatic region, and look at that. It adds up to about, if this goes up to 8, and that's 2, that's 10. That's pretty good. And then here, you'd probably at first initially guess this is a 1 hydrogen singlet. The alcohol, they usually don't get coupling through the oxygen, but you can if the oxygen is an alcohol that has intermolecular hydrogen bonding. For some reason, that those type of groups will create coupling. So it's going to couple. It's going to be 1 hydrogen doublet because it's going to couple to this one right here. Now this guy, if it can couple through the oxygen, then it's a 1 hydrogen doublet as well. And what do you know? We got 2 1 hydrogen doublets. Isn't that nice? The signal at 3.3, yeah, I didn't even have to integrate that, huh? That's nothing from our molecule. What that is water. So deuterated DMSO, D6 DMSO, it looks like this. There's 3 deuteriums on that side, 3 deuteriums on that side, so that's what deuterated DMSO looks like. And it's very hygroscopic. It picks up moisture. When I have the cap open there and I was getting sample out of it, moisture in the air was getting in there. And so the moisture creates a 2 hydrogen singlet for that water signal, and it shows up at 3.33 parts per million. So when you use DMSO, especially if it's not a brand new bottle, you expect water there. So I'm going to actually delete that last integral. I'm going to hit L for the last one because I don't need to integrate the water signal. Another thing about deuterated DMSO is it's only, I think it said it was 99.5% isotopically pure on the bottle. So what that means is there's like 0.5% that's got 3 deuteriums on one side, but only 2 deuteriums on the other. So it's got 1H here. And that hydrogen, it shows up as a 1 hydrogen pentet. You're thinking pentet, why is that? because deuterium, it has 3 spin states, and it follows a 2n+1 rule, not the n+1 rule. So it's 2 times 2 neighbors plus 1, that equals 5. That will show up at about 2.5 parts per million. Let's see if we see it. If you're looking close here, 2.5, and I start to zoom in. Yep, that right there. That's the deuterated. That's the DMSO D5, not D6. It has 1 hydrogen. So we're seeing a solvent signal. This little guy on the side, I'm not sure what that is. Maybe that's. I don't know what it is. But yeah, pretty cool, huh? It's a nice spectrum. This water signal, we don't assume it's from our sample, we assume it's from the DMSO bottle, so our sample's clean. Looks really nice. I'll screen capture this one and share it with you guys. Oh, before I do that though, before I screen capture, I'll show you how to be efficient. I'll start the carbon scans and then I'll screen capture. So start the carbon scans, I'll go NU space C13, enter, and then ZG, enter. So let's start doing those 12 scans. While it's doing those 12 scans, I'll screen capture this guy.